Hello everyone. I'm Wei-Ming Wu, an intern at Fang Medical Device Enterprise. Today, I want to introduce my project for this summer. The topic is, optimizing the accuracy of face recognition based on YOLOv5. Here is the outline. I'll first introduce the motivation for the experiment, then explain how to conduct it, and then analyze and discuss the results after obtaining them. Finally, there will be the conclusion and future outlook. Face recognition is a technology based on biometric recognition. It uses the characteristics of the face to authenticate and identify. With the advancement of science, this technology plays an important role in modern society. It is now widely used in security recognition systems or social media applications like Apple Face Unlocking. Face recognition in future development is pervasive and has infinite potential, so I chose this topic to study. The model YOLOv5 was chosen because 1. Flexibility. YOLOv5 provides various model size options, such as YOLOv5N, YOLOv5S, YOLOv5M, etc., and users can choose the appropriate model according to their application needs. This is one of the most advanced real-time object detection models. Compared with some newer models, YOLOv5 has more complete accessories, mature technical foundation, and stable performance, which are the advantages of YOLOv5 at present. The goal of this experiment is to significantly improve the accuracy of face recognition by tuning the model, especially in different environments. We all know that there are experimental groups and control groups for experiments, so I divided the experiment into 4 groups, one of which is the control group, and the rest are Big Data Group, the Best Epoch Group, and integration groups that use the above methods. I have used RoboFlow to build datasets in the following. Let's start with the control group, where I use my face as the test subject. I use the following command to train, and I set the epoch to 20. Then, there is the big data group, and I added more images based on the data set of the control group. I took photos indoors and outdoors, randomly blocking faces and shooting from different angles. Hopefully, this will increase data enrichment. The epoch is 20. Then there is the best epoch group, where patience 10 implements the early stop method, sets the patience to 10, and stops the training when the model's verification loss does not improve in 10 consecutive epochs so that the optimal epoch can be found to be 45. Then, there is the integration group. This group used the early stop method with a large data set to train, and the optimal training epoch is 35. Once these 4 groups are done, validation indexes are used to compare the degree of optimization. Here is the table of the results. You can see the part of the highlight. The accuracy of the large dataset group was lower than the control group, which will be discussed later. Then, the best performer was the best epoch group. There are several reasons why the accuracy of the big data group is lower than the control group. First, larger datasets may contain more noise factors that can affect the training of the model, resulting in degraded model performance or new data that is too diverse, which can lead to poor model performance in some cases. Second, data distribution differences. For example, if the model is initially trained on indoor face images and later adds a set of face images taken outdoors with bright light or shadows, the feature distribution of these new images is significantly different from the original image. The model may be confused by this difference between the old and new data, making it difficult to accurately identify in all cases. Third, overfitting or underfitting, because when we use a larger dataset, we may need more epochs for the model to learn adequately, and it may not perform as well as expected if the epoch is insufficient. In addition, the reasons why the accuracy of the integration group is lower than the best epoch group may be the following points. First, if the patience is set too low in the integration group, it may cause the model to stop training prematurely without fully learning the features of the data. Conversely, setting too high may lead to overfitting, so the setting of patience needs to be adjusted on a case-by-case basis. Second, randomness and luck. There is a randomness in the training process, and the difference in the results of these runs may only be caused by these random factors. If the results are unstable, it may be necessary to run multiple times to get the average performance. Third, the training data does not match the augmentation strategy. For example, if the color of the image is often changed during the data augmentation process, but the color information is a key feature in the actual application, then such augmentation may weaken the recognition ability of the model. Furthermore, the best epoch group achieves the highest F1 score and precision, which illustrates that the importance of finding the optimal epoch to achieve an accurate and balanced model. We have compared the results with the literature, and our findings differ slightly from the conclusions reached in The Unreasonable Effectiveness of Data, which emphasizes the importance of the dataset size. However, our experiments state that more careful epoch adjustments may have a more significant impact on F1 scores and precision than data size adjustments alone. In conclusion, this experiment shows that optimizing the number of epochs is the key to enhancing the performance of YOLOv5 in facial recognition. However, increasing the dataset size and applying all available techniques can improve the model performance. We still have to monitor and manage to avoid overfitting, so future research can further explore the impact of different data augmentation techniques on model generalization and use larger datasets for experiments in more different facial recognition scenarios. The above are references for the presentation today. Thank you all for listening.